Welcome to this problem walkthrough. In this video, we'll be tackling LeetCode problem number 1265, print immutable linked list in reverse. This problem brings an interesting challenge due to the immutability constraint, which means we can't modify the linked list directly. We'll explore the problem, consider different approaches, and arrive at an efficient solution. Let's dive in. In this problem, we are tasked with working with an immutable linked list. Now, immutability means that the structure of the list cannot be altered in any way. For instance, you cannot insert new nodes, delete existing ones, or modify their values. Instead, the goal here is to print the values of the nodes in reverse order. To achieve this, we are provided with a specific interface for the immutable linked list. The immutable list node class has two key methods: printValue, which directly prints the value of the current node to the console, and getNext, which gives you access to the next node in the list. Your job is to implement a function, printLinkedList in reverse, which takes the head of the immutable linked list as input and prints its values in reverse order, adhering to the constraints of the list's immutability. Now, let's break down the inputs and outputs for this problem. The input to our function is the head of the immutable linked list, represented as an instance of the immutable list node class. The output, on the other hand, is simply the printed values of the nodes in reverse order. It's important to note that the function itself does not return anything. Its sole purpose is to print the values to the console, one value per line, starting with the last node and ending with the first. For example, if the linked list contains the values 1, 2, 3, 4, the output should be 4, 3, 2, and 1, each printed on a new line. In this case, since the list is immutable, you cannot reverse it directly, so you'll need to rely on alternate approaches to achieve the desired output. To provide another example, consider a linked list with values 10, 20, 30. Here, the output would be 30, followed by 20, and then 10, each printed on a new line. The challenge lies in how you approach the problem without modifying the list. For instance, the getNext method allows you to traverse the list in its natural forward order, but you'll need to find a way to reverse the printing sequence. For a single node list, such as one containing only the value 42, the output is straightforward: you simply print 42. This demonstrates that the function must handle both simple and complex cases while adhering to the constraints of immutability. The problem also comes with several constraints to keep in mind. First, the number of nodes in the linked list can range from 1 to 10,000. So your solution must be efficient enough to handle the upper limit. Each node's value falls within the range of -1 million to +1 million. A key restriction is that you cannot use extra space for data structures that scale with the size of the list. This means you cannot store all the node values in a list or stack to reverse them later. Recursive solutions are allowed, but they must be able to handle the maximum depth of recursion without exceeding system limits. For edge cases, ensure your function works correctly for a single node list, handles the largest possible list size efficiently, and correctly processes lists with negative values, such as -1, -2, -3. These constraints make it essential to carefully choose an approach that balances efficiency with the immutability requirements. To tackle the problem of printing an immutable linked list in reverse, we must navigate the constraints imposed by immutability. Since we cannot modify the list or traverse it backward, we need alternative strategies to reverse the order of nodes. One straightforward approach is to use recursion. Recursion naturally lends itself to reverse traversal because each recursive call processes the next node first, and only after returning from the call stack do we handle the current node. To implement this, we define a recursive function that takes a node as input. If the node is null, we stop the recursion. Otherwise, we recursively call the function for the next node and print the current node's value after the call returns. While this approach is conceptually simple and matches the reverse order requirement, it has a significant downside. For large linked lists, the recursive call stack grows linearly, consuming O(n) space and risking a stack overflow. This limitation makes it less suitable for very large inputs, despite its implementation simplicity. An alternative and more robust approach involves using a stack, which naturally supports reverse order processing with its last in first out behavior. Here, we first traverse the list and push each node's value onto the stack, capturing the forward order of elements. Once the traversal is complete, we then pop each value from the stack, which outputs the elements in reverse order. This method achieves the goal without relying on recursion, avoiding the stack overflow risk associated with deep recursion. In terms of complexity, the time required is O(n) for both traversing the list and performing stack operations. The space complexity is also O(n) due to the storage of node values in the stack. While this approach consumes additional memory, it is more reliable for larger linked lists and maintains clarity in implementation. There is also an alternative divide-and-conquer strategy, where we recursively reverse print smaller segments of the list. However, this adds unnecessary complexity compared to the stack-based approach and typically does not offer performance advantages. The divide-and-conquer approach involves splitting the list into two halves and recursively reverse printing each segment. First, we identify the midpoint of the list. Then, starting with the second half, we recursively process and print its elements in reverse order before handling the first half in the same manner. While this method works, it introduces additional overhead without offering clear benefits over simpler techniques like using a stack. Both the time and space complexities remain O(n), but the added complexity makes the solution harder to implement and less intuitive. After evaluating these options, the stack-based approach emerges as the most effective strategy. It avoids recursion-related limitations while offering a straightforward and scalable solution. The key insight here is that the immutability of the list necessitates auxiliary structures or recursion. A stack aligns perfectly with these requirements, providing an efficient and manageable way to reverse the traversal. The stack-based solution stands out as the best choice for several reasons. Unlike recursion, it does not risk stack overflow, making it more robust for large inputs. The divide-and-conquer method, while creative, introduces unnecessary complexity without improving performance or efficiency. The stack approach strikes the right balance between simplicity, efficiency, and scalability. Of course, the trade-off is that it requires additional space proportional to the size of the linked list. However, given the constraints of the problem, this is an acceptable compromise. While recursion might seem more elegant in terms of code structure, its inherent limitations make it less reliable for this scenario. By choosing the stack-based strategy, we ensure the solution is not only optimal but also easy to understand and maintain, making it the most practical approach to solving the problem. In this problem, we are tasked with printing the elements of an immutable linked list in reverse order. The key challenge here is that the linked list is immutable, which means we cannot modify its structure or traverse it backwards. The only method available to us is getNext, which allows access to the next node in the list. This limitation forces us to think creatively about how to reverse the output without directly modifying the list or using an excessive amount of memory. One effective approach to tackle this is through recursion, which allows us to traverse the list to the end and then print the nodes in reverse order as the recursive calls return. Let's break this down step by step to understand how recursion helps achieve this in an efficient and elegant way. The recursive solution works by delaying the print operation for each node until all the subsequent nodes have been processed. First, we need to define a base case for the recursion. If the current node is null, we stop the recursion, as we've reached the end of the list. For the recursive case, we retrieve the next node using the getNext method and call the function recursively with this next node. Once the recursion reaches the base case and starts to unwind, we then print the value of the current node. This ensures that the nodes are printed in reverse order of their appearance in the list. For edge cases, if the list is empty, the function will do nothing since the head is null. If there's only a single node, the function will print that node after hitting the base case. In terms of complexity, this approach visits each node exactly once, resulting in a time complexity of O(n). However, the recursion stack requires O(n) space, which is an important factor to consider for very large lists. The beauty of the recursive approach lies in how naturally it reverses the order of operations. As the recursion unwinds, it allows us to print the nodes in reverse order without explicitly modifying the list. This makes it a perfect fit for the immutability constraint, as we don't need to alter the data structure or use any external storage. However, the trade-off is the O(n) auxiliary space used by the recursion stack. This works well for lists of moderate size but could become a limitation for extremely large lists due to the risk of stack overflow. The recursive approach also eliminates the need for additional data structures, relying solely on the call stack to manage the order of nodes. Here's a Python implementation of the approach. the function checks if the current node is null and returns in that case. Otherwise, it moves to the next node recursively and prints the current node's value after the recursion has completed. This simple and concise solution adheres to the problem's constraints while maintaining clarity and efficiency. To visualize this process, imagine a linked list with nodes containing the values 1, 2, 3. The function starts with the first node, node 1, which has the value 1. It calls itself recursively with the next node, node 2, which has the value 2, and this chain continues until the last node, node 3, which has the value 3. At node 3, the getNext method returns null, signaling the base case. The recursion stops, and as it begins to unwind, the values are printed in reverse order. First, the value of node 3, 3, is printed, followed by node 2, 2, and finally, node 1, 1. While this approach is optimal for simplicity and adheres to the immutability constraint, an iterative solution using a stack could be considered as an alternative to avoid the potential risk of stack overflow with very large lists. In summary, the recursive approach effectively solves the problem by leveraging the natural reversal properties of recursion, balancing simplicity and adherence to constraints, with the trade-off being its O(n) space complexity. This solution to LeetCode problem number 1265, print immutable linked list in reverse, leverages recursion to print the values of an immutable linked list in reverse order without modifying the list. Explanation. 1. Problem constraints. The linked list is immutable, meaning we can only move forward using the getNext method, and the value of a node can be accessed via the printValue method. We cannot use common techniques like reversing the list in place or converting it to an array. 2. Recursive approach. Recursion is a natural fit for this problem. By deferring the print value calls until after we have traversed to the end of the list, we effectively print the values in reverse order as the recursion unwinds. 3. Implementation details. The print linked list in reverse function defines a helper function reverse print for recursion. The base case for the recursion is when the current node is none, indicating the end of the list. In this case, we return without taking any action. Otherwise, the function recursively calls itself with the next node, node.getNext, moving one step forward in the list. After the recursive call returns, the printValue method is called on the current node to print its value. This ensures the values are printed in reverse order, from the last node back to the head. For efficiency, since the recursion depth is proportional to the length of the list, O(n), and each recursive call involves a constant amount of work, the time complexity is O(n). The space complexity is also O(n) due to the call stack. 5. Edge cases. If the list is empty, head is none, the function exits gracefully without printing anything. The function handles lists of all lengths, including a single node. This implementation is clean, concise, and adheres to the constraints of immutability, making it well-suited for the problem's requirements. This is the Java implementation of LeetCode problem number 1265, print immutable linked list in reverse. The logic mirrors the Python implementation, using recursion to traverse to the end of the list before printing values in reverse order. Key differences include Java type declarations, the use of an interface for the immutable list node, and a private helper method for recursion. The solution adheres to Java conventions and ensures clarity and simplicity. In this problem, we are asked to print the values of an immutable linked list in reverse order. The key challenge here is that the linked list is immutable, meaning we cannot modify it or store its elements in additional data structures like arrays or stacks to reverse the order. Instead, the nodes of this linked list implement the immutable list node interface, which provides two methods, getNext, to access the next node and printValue, to print the current node's value. For example, consider a linked list with 3 nodes, 1, 2, and 3. Initially, the head points to the first node with value 1. We begin by calling the reverse print function on this head. Inside the function, we first process the node with value 1, and then call reverse print recursively on the next node, which has the value 2. Next, the recursive call processes the node with value 2. Here, the function again calls reverse print recursively, this time on the next node, which is the node with value 3. When we reach the node with value 3, the function makes another recursive call to its getNext method, which now returns none since this is the end of the list. At this point, we hit the base case of the recursion, or the function will simply return because there are no more nodes to process. Now, as the recursion backtracks, we print the values stored in each node in reverse order. First, the value 3 is printed because we are backtracking from the deepest recursive call. Then, we move to the previous node and print the value 2. Finally, we return to the very first function call and print the value 1. The final output for this example is the sequence 3, 2, 1. Now let's take a look at another example, this time with a linked list consisting of just one node. Here, the node has a value of 42. The process is similar to the previous example, but simpler due to the smaller size of the list. Initially, the head points to the single node with value 42. The reverse print function is called on this head, and in the first recursive call, the function processes this node and makes a call to getNext. Since this is a single node list, getNext returns none, and the base case is reached. The recursion terminates, and as we backtrack, the value 42 is printed. Thus, the final output for this example is simply 42. For a more complex scenario, consider a linked list with 5 nodes, 10, 20, 30, 40, and 50. Here, the process of recursion plays out over multiple layers. We start by calling the reverse print function on the head of the list, which points to the node with value 10. The function continues making recursive calls, traversing from the current node to the next, until it reaches the last node with value 50. At this point, the recursion stack is fully built, and it holds references to the nodes in the order they were traversed, 10, 20, 30, 40, and finally 50. When the getNext method of the last node returns none, we hit the base case, and the recursion begins to unwind. As we backtrack through the recursion, we print the values of the nodes in reverse order. The first value printed is 50, which was the last node encountered during the traversal. The function then backtracks to the node with value 40 and prints it, followed by 30, 20, and finally 10. This reverse order printing is achieved because the function delays the print value, calls until the recursion starts unwinding. The final output for this example is the sequence 50, 40, 30, 20, 10. By traversing the list forward and leveraging the call stack to store the order of nodes, we can achieve reverse order printing without using any additional data structures. This ensures that the solution is both space efficient and adheres to the immutability constraints. There are a few key insights to highlight about this approach. First, it relies on recursion to traverse the list all the way to the end before beginning the reverse order printing during backtracking. This recursive approach effectively uses the call stack as a temporary storage mechanism, maintaining the order of the nodes without relying on any extra data structures. Second, while the recursive approach does use O(n) stack space, it avoids additional space proportional to the size of the list, which aligns with the problem's constraints. Third, the base case of the recursion is reached when the node becomes none, at which point the function simply returns and starts unwinding. Finally, the solution respects the immutability of the linked list by not altering or storing the nodes, ensuring that all operations are performed in place and directly on the nodes provided. To analyze the time complexity of the recursive solution, we start by looking at the recursive traversal. The function makes a recursive call for each node in the linked list. If there are n nodes, this results in n recursive calls. Now, since each call to node.getNext is a constant time operation, O(1), the total cost for traversing the entire list becomes O(n) O(1), which simplifies to O(n). Next, during the backtracking phase, the node.printValue function is called once for each node. This operation also takes constant time per node, O(1). With n nodes, this results in another O(n) for the printing phase. Combining these two parts, the overall time complexity of the solution becomes O(n) plus O(n), which simplifies to just O(n). This demonstrates that the recursive approach is linear in time complexity, as it processes each node only once during traversal and printing. Now turning to space complexity, the key factor is the recursive stack usage. In this solution, the depth of the recursion equals the number of nodes in the linked list, n. Each recursive call requires a constant amount of memory, O(1), for local variables in the function's context. Therefore, with n recursive calls, the total memory footprint for the recursion stack is O(n) O(1), which simplifies to O(n). Importantly, the solution does not use any additional data structures or extra memory beyond the recursive stack. Since no auxiliary space is allocated for storing values or other operations, the overall space complexity is determined solely by the recursion stack, and it is O(n). To put this solution in perspective, let's compare it to a brute force approach. A naive method would involve traversing the linked list while storing all the node values in a separate data structure, like a list or stack. After storing the values, you would then print them in reverse order. While this approach also requires O(n) time for traversal and printing, it introduces an additional space requirement of O(n) to store the values. In contrast, the current recursive solution achieves the same time complexity, O(n), but avoids the need for extra space by leveraging the recursive call stack for backtracking. This makes the solution more memory efficient in terms of auxiliary space, even though the overall space complexity remains O(n) due to the recursion stack. Finally, let's analyze the best, worst, and average cases for this solution. In the best case scenario, the linked list contains only one node. Here, both time and space complexity are reduced to O(1), as only one recursive call is made, and no significant recursion depth develops. On the other hand, the worst case scenario occurs when the linked list has n nodes. In this case, the time complexity is O(n), because we need to traverse all n nodes and print their values. Similarly, the recursion stack grows to a depth of n, resulting in a space complexity of O(n). For an average case, with a typical linked list of length n, the time and space complexities remain O(n), as they depend solely on the number of nodes. Mathematically, the recurrence relation for time complexity can be expressed as T(n) equals T(n1) plus O(1). Solving this gives T(n) equals O(n). Similarly, the space complexity stems from the linear growth of the recursion stack, confirming it as O(n). When working with immutable linked lists, there are several common mistakes to watch out for. First, attempting to modify the structure of the list is a frequent error. For example, trying to reverse the list directly or save the nodes into a new list for manipulation violates the immutability constraints of the problem. Remember, immutable data structures cannot be changed, and any attempt to do so will lead to errors. Another pitfall is ignoring memory constraints. While it's tempting to store all the nodes in a large array or list, this approach can fail for larger inputs due to excessive memory usage. Many problems like this implicitly require you to optimize for space, often aiming for O(1) or O log n space complexity. Lastly, neglecting edge cases such as single-node lists or extremely large lists can result in runtime errors. These scenarios are commonly tested in coding interviews, so it's important to account for them in your solution to avoid unexpected failures. Another mistake to avoid is misunderstanding how to interact with the API provided in the problem. For instance, if the problem specifies a helper function like printValue, you must use it as intended. Attempting to access the value directly or bypass the function violates the constraints and can disqualify your solution. The helper function is there for a reason; it's the only approved way to interact with the data. Additionally, using recursion without considering its limitations is problematic. A naive recursive approach might look elegant but can lead to stack overflow for deep linked lists due to limited recursion depth. In such cases, an iterative stack-based solution is often safer. Always be mindful of the trade-offs between simplicity and scalability when choosing your approach. To excel in interview problems like this one, it helps to recognize key patterns. Immutability often requires you to think creatively, such as using recursion or an external stack to simulate reverse traversal. Effective use of external storage can help you work around the immutability constraints, but you need to do so judiciously to avoid unnecessary complexity. Interviewers also value your ability to discuss trade-offs. For instance, recursion might lead to cleaner code, but it comes with the risk of stack overflow, especially for deep linked lists. On the other hand, an iterative stack-based approach uses more memory but is safer and more scalable. It's also important to ask clarifying questions during the interview. For example, confirm whether constraints like memory usage or recursion depth limits are strict requirements for the solution. Finally, always aim to optimize your approach based on the problem's constraints. If the problem specifies O(1) space complexity, avoid solutions that rely on additional data structures even if they seem easier to implement. If you're looking to deepen your understanding, there are several related problems worth exploring. For example, LeetCode number 206 focuses on reversing a standard linked list, which can help you practice fundamental linked list manipulations. In LeetCode number 234, you'll work on checking if a linked list is a palindrome, often using fast and slow pointers combined with a stack. Meanwhile, LeetCode number 143 involves rearranging a linked list by alternately picking nodes from the start and end, a problem that tests your ability to manipulate pointers effectively. Finally, LeetCode number 369 challenges you to add 1 to a number represented as a linked list, which requires careful traversal from the end to handle carry propagation. These problems reinforce similar concepts and give you a chance to tackle variations of linked list manipulation in different contexts. There are several alternative approaches you can use to solve the problem, each with its own trade-offs. The recursive approach is a common choice. Here, you traverse the list to the end using recursion, then print the nodes during the unwinding phase. This method is elegant and simple to implement, but it comes with the risk of stack overflow for very deep linked lists. Another option is the stack-based approach. In this method, you traverse the list while pushing all nodes onto a stack. Then, by popping the nodes from the stack, you can print them in reverse order. While this approach is safe for deep lists, it requires extra space to store the stack, which may not be ideal in space-constrained scenarios. Finally, the two-pass approach, if applicable, involves making one pass to count the nodes and a second pass to access them in reverse using the provided API. This approach avoids recursion and stack usage but requires 2 full traversals of the list. Each method has its advantages and limitations, so choosing the right one depends on the specific constraints and requirements of the problem. Thanks for joining today's session. We reviewed strategies for solving the print immutable linked list in reverse problem and explored key concepts like recursion and stack-based approaches. Remember, practicing problems with immutability constraints will sharpen your skills for interviews and real-world challenges. See you next time, and don't forget to like and subscribe. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!